It's time to learn about balancing chemical reactions and what these chemical equations are. So, chemical reaction is a process where one or more chemicals are changed into one or more new substances. And the chemical equation is just a mathematical concept of what happens in the reaction. The reactants are always on the left side, and the products are always on the right. And the arrow, there's always an arrow between the reactants and products. Looks like this right here. So these would be our reactants. These are our products. Here's the arrow. And the numbers in front, this actually doesn't have any numbers in front yet because it's not balanced. And the numbers in front have a name, and the name is coefficients. All right, you can read the rest of this on your own. All right, so this is an unbalanced chemical equation. And in order to balance this, we look and we see there's one sodium here and one here, but there's two fluorines here and only one here. So we have to balance the fluorines. We never put coefficients in the middle of a chemical. I couldn't put a coefficient in between Na and F. I can only put them in front of a chemical. So I have to stick a 2 in front of the Na in order to have two F's on each side. And then I need to put a 2 in front of this Na in order to balance the sodiums that are right here. So this is our overall balanced equation. This is what it'll look like. Okay, some general rules. This will help you. So there's going to be a bunch of reactions you're going to balance. And one of the rules, first thing you should balance is the elements that appear only in one substance on each side of the arrow. So in this one, each substance appears only once. Oh no, if you look at this, iron is appearing twice on the left. So we wouldn't do iron first. And notice sulfur is twice on this side, so I wouldn't do sulfur first either. You might start with the hydrogens, but those are already balanced. It appears that they're already balanced. Oh wait, oh my goodness, sorry. This is one reaction. This is a separate reaction. Oh, I'm not seeing clearly here. Okay, so each element is only appearing once on each side. Here again, only once on each side. Here there's O's all over the place. You'd kind of do the O's last. And then over here, the O's are appearing twice. The oxygens are appearing twice here, so you do the oxygens last. Okay, so that's what that first rule is telling you. So after you do the elements that appear only once, then you do elements that appear at most 3 times, and then do everything else. So typically we will balance by and slash. Okay. I will do some of the first ones with you. So you look at this and notice there's 8 sulfurs here and only 1 here. So what do you need to do? What are we going to put? We're going to put an 8 in front of here. And okay, so we put an 8 here because there's 8 S's and 8 S's. Now notice the Fe's. So what do I need to put over here? An 8. And this would just be a 1. And that one is now balanced. Let's go to this one. And you can pause this and do these all on your own if you'd like to just try. So the H's look like they're balanced, but the O's, there's 1 O here and 2 O's there. So what do I need here? I need a 2 and a 1 there. And now the H's. So here I have 2 times 2 is 4 H's. So how do I make this 4? I put a 2 in there. Okay. Onto this one. Let's see, Fe. Okay, it looks like I would need a 2 here because there's 2 Fe's here and only 1 here. Now the H's look okay. They look okay. Oh dear, but this O, there's 1 O here and there's 3 here. Sometimes you have to go back and do other elements that you've already done. Sometimes you don't. So now there's 3 O's here and only 1 here. So what do we put in here? A 3. And now we can do our H's. So 3 times 2, we have 6 H's here, so I need 3 right there. and this is a 1. Okay, this one might look a little tricky, but it's actually, if you look at it, it's pretty straightforward. Notice we have a CuSO4, that's a copper 2 sulfate, and there's a copper 2 sulfate right here. This dot means that these are called hydrates. So there's a copper 2 sulfate with 5 waters attached to it. These are written differently, hydrates. The 5, we don't write as a subscript, we write it in front. When you see this little circle here, and then a number with waters, it's the only time you'll see this dot here. It's called a hydrate. It says I have 5 waters. So what do I need over here? 5. And it looks pretty balanced to me. 1 and 1. Okay. Over here, let's see, carbons, hydrogens. There's oxygens all over. We don't want to do those first. So we can do the carbons first. There's 3 here, so I put a 3 there. Again, pause this and just do this on your own and fast forward to get the answers. Now, I still don't want to do the oxygen, so hydrogens. I have 8 here, 2 here, so I need a 4. All right. Now the oxygens. 3 times 2 is 6, plus 4 times 1. 6 plus 4 is 10. And over here, I have 2. How do I make this 10? I put a 5 in there. And this is now balanced. And the last one, the answers are underneath here. I'm not going to go over it with you, but here are your answers. Whoops. There you go. These are the answers for the last one. Okay, you'll have more time to practice balancing in class. So, amounts of reactants and products. That's our next section. And there's a special word for figuring out amounts of reactions and products in reactions. It's called stoichiometry. Stoichiometry is defined as the quantitative study of reactants and products in a chemical reaction. And we're going to use another song for this. And the song goes, grams to moles, use molar mass. Moles to molecules, moles to moles, use the reaction coefficients. Moles to grams, use molar mass again. And that's how you do stoichiometry. All right, so here's our song, and we will follow the song. And this is a visual of what the song means. So if you have grams of A, you can convert to moles of A using molar mass. Now, if A and B are different substances, to go from moles of one chemical to moles of another chemical, we use the reaction coefficients. Remember, the coefficients are these numbers in front. Those are your coefficients. And if you want to go from moles of chemical B to grams, moles to grams, use molar mass again. And remember, molar mass is just adding up those numbers from the periodic table. So here's a problem. We have 2.9 grams of hydrogen that reacts with excess oxygen, so we don't care about the oxygen. We'll learn about this excess concept later. What mass of water will form? You should know water is H2O by now. And you're given a balanced reaction. So we had grams, starting with grams, so it's grams to moles, use molar mass, and we're trying to get to water, so we'll go moles of hydrogen to moles of water using the reaction coefficients, and then we'll go from moles of water to grams of water using molar mass. Okay, so here's what it would look like right here. Okay, so this is our grams to moles, use molar mass. Moles to moles, use the reaction coefficients. Moles to grams, use molar mass again. And this is how you do stoichiometry. Okay, whenever you use molar mass, it is always grams per mole, which means grams per 1 mole. And you can use the molar mass right side up or upside down because it's just a conversion factor. Okay, another example. We have 3.5 moles of oxygen and it reacts with excess hydrogen. What mass of water will form? So this time, note, we're starting with moles. So in terms of the song, we start at moles to moles, use the reaction. You can enter this song anywhere. And then you can end it here or here. If you just ask for moles, you stop at this place. Now this problem is, starting at moles. Where are we? We did that problem already. We're starting with moles of oxygen, and we're trying to get to grams. Mass is grams. You should make a note for yourself. Mass means grams. So, starting with our moles. Moles to moles, moles to moles. Use the reaction coefficients. So, oxygen has a 1 right there. We don't write the 1s. We don't have to. And water has a coefficient of 2. So, moles to moles, moles to moles. Use the reaction coefficients. Moles to grams, use molar mass again. Here's the molar mass of water. And that's how you do stoichiometry. Notice we had 2 sig figs, so I have to round this to only 2 sig figs. All right, next 2 problems. Try these on your own. The solution is going to appear in a moment. So we're looking for moles of ammonia. We're starting with moles of hydrogen. This is easy. We're starting with moles, so it's just moles to moles, moles to moles. Use the reaction coefficients. You can pause and do this on your own, but here's your solution. So we have moles of hydrogen. We're starting with our 3.2 moles of hydrogen. Moles to moles, moles to moles. Use the reaction coefficients. And remember, you always have to cross cancel, so moles hydrogen have to start on the bottom. And we're going to moles of ammonia. We get 2.13, but we only keep 2 sig figs, so the final answer would be 2.1 moles of ammonia. Now, another one. Notice we're starting with our moles, moles of ammonia, and this is ammonia right here. We're starting with moles, and we said to produce, so it has to be a product. Oh, this is the only product, so this must be ammonia. All right, so we start with our pause this and do it on your own. I'm about to give you your explanation. We'll start with our moles ammonia right here. Moles to moles, moles to moles. Use the reaction coefficients. 2 ammonias to 1 nitrogen. And then moles to grams, asked for grams of nitrogen. Use molar mass again, and that's how you do stoichiometry. 3 sig figs, 3 sig figs. We're happy. Okay, this is a little more complicated. Limiting reagents. So sometimes you're given both reactants, amounts of both reactants. In this case, one will get upped, and that is termed the limiting reagent. The substance left over is called the excess reagent. And there's a bunch of steps you're going to have to follow for these. And you just have to learn how to do this. You have to do a couple examples, and then we'll do more in class. And you learn this through practice. It makes logical sense, but it's a series of steps. Okay, so here are your steps, and we're going to go through the example right here. Here's your problem. You know you have a limiting reactant problem because we are given both hydrogen and oxygen. Those are both reactants. We're given 2 reactants. You immediately say, oh, limiting reactant. I need to calculate my moles of each reactant. That's step 1. So this is just showing you your gram to mole calculation. Moles of hydrogen, moles of oxygen. We write the moles of each reactant directly below the reaction. So I had 2.5 moles hydrogen, 0.25 moles of oxygen. We write that right underneath the reactants. Now, we divide the moles of each reactant by its coefficient. So the 2.5 I divide by 2, the 0.25 I divide by 1. This is telling you how many times the reaction could go through for each reactant. So for the oxygen, this reaction could occur 0.25 times in terms of the molar amounts, because it's 2 to 1 to 2 molar amounts. I only have 0.25 of these in terms of if it was on a 1 molar basis. Now the hydrogen, I had 2.5 moles, I divided by 2. So on a per mole basis, I could have 1.25 of these reactions go through. The one that gives you less, a smaller number here, is your limiting reactant because it's going to get used up. The oxygen can only go through this 0.25 times. So once we use that up, there's no more oxygen, the reaction has to stop. So that was step 4. We identify the smallest number right here. So first you get your moles, put them underneath, divide the moles by the reaction coefficient, and the smaller number is your limiting reagent. So hydrogen is in excess. So to get your amount of product produced, we use the moles of the limiting reactant, and we get to product produced. And we asked for mass. We asked for mass here, so we need to get mass of water produced. We used our limiting reactant, which was the oxygen, and we had 0.25 moles of oxygen. And we just convert to mass of water, because that's what it was asked for. So moles to moles, moles to moles, use the reaction coefficients, moles to grams, use molar mass again, and we get 9.01 grams of water. Okay, last step. So I've answered who's the limiting reactant. I've answered what's the mass of water formed. Now I'm going to get the mass of excess reactant left over. Well, I first have to figure out how much was used. So we're going to calculate the moles used by converting the limiting reactant to the excess reactant. I had 0.25 moles of water. I have to find out how much hydrogen I use to react with that water. And just looking at the stoichiometry, I use 1 to 2, so 0.25, I just multiply it by 2, and you should see I'm going to use 0.5 moles of hydrogen. But this is your calculation, because a lot of students are still iffy on all of this information. So, oops, not right there. Here we go. So we have 0.25 moles of oxygen. We go from oxygen to hydrogen, because oxygen was a limiting reactant. And we find out that we're going to use 0.5 moles of hydrogen. So I know how much hydrogen is used. Well, if I started out with 2.5 moles and I used 0.5, how much do I have left? 2. So here, we're still on step 6. We find out how many moles we used. We subtract that from how many we started with, and that's how many moles are left over. If you ask for grams, we have to convert that leftover amount to grams. And let's see, what were we asked? Find the mass of excess reactant left over. We have to go to grams. So we started with 2.5 moles. We used 1/2 mole. We have 2 moles left over. We're asked for the mass of excess reactant, so I have to convert my 2 moles of hydrogen to grams. And we get 4.04 grams left over. We had 3 sig figs. We keep 3 sig figs. All right, your turn. You should try this one on your own. I've blocked out the answers from you. So you do step 1. You convert both reactants to moles. You should do that. You should pause this. I'm about to show you the mole conversions, but you should not just copy this. You should do this on your own. Oops. Convert your grams to moles. We get a 4 hydrogen to nitrogen. And the next step, we write the moles right under the reaction, and then we're going to divide the moles by the coefficients. And you should pause and do this on your own. If you get stuck, it's okay to watch the video, but do this on your own, see what you get. We write the reactants directly underneath, divide by the coefficients, and the next step says check which one is smaller. Well, you can pause, try this on your own. Here are your answers. Obviously 1.3 is smaller than 2, so hydrogen is our limiting reactant. So we've answered the question, what's the limiting reactant? The next step is to find out how many moles of ammonia are formed. Oh, did I go all the way to? I'm seeing I went all the way to grams. So the answer you're about to see is in grams, but I will in words tell you what the moles are. And always pay attention to what the question asked. So the question says, how many moles of ammonia formed? Well, for moles of ammonia, it's just 4 divided by 3 times 2. 4/3 of 2. I believe that's 1.67. 7 moles ammonia. No, that is not 1.67. It is 2.67. I just put it in my calculator. Okay, so the question asked for this right here. So I didn't need to do the grams. I didn't need to go all the way there. It's just moles. And now we need the mass of excess reactant left over. Remember, you find out how much you used based on the limiting reactant. Hydrogen was limiting. Again, pause, try this on your own. I have to figure out how much N2 was used. So, and I subtract that from how much I started with. And then I will convert that to grams because that's what was asked for, and here it is. So we had 2 moles of N2. We're going to use 1.33. We convert the hydrogen to nitrogen, and it's a 3-to-1 ratio. So 4 divided by 3 times 1 is 1.33. So 2 minus the 1.33 is 0.67 moles left over. Convert that to grams, and we get 9.4 grams of N2 left over. All right, last topic for this video is reaction yield. So when we have reactions occurring, there's often side reactions, or we don't completely collect all of the product. So we have something called a theoretical yield. That's how much you should form in a reaction. And the actual yield is how much you actually collect. And then chemists use this thing called a percent yield. It's the actual yield over the theoretical yield times 100. And that gives you your percent. Remember, percent is just part over total. So here's an example. Theoretical is what we should form. So we do the calculation based on the given information. This right here is how much was produced. That's the actual yield. You're given the actual yield in these, not the theoretical. Theoretical, we use stoichiometry to calculate. So 4.5 grams, we're going to convert that to grams of water. Pause this and do it on your own. Here's your solution. So I should have formed 40.1 grams of water, but I only formed 38.3. So I do the actual over the theoretical. The actual is 38.3. You should be able to do this on your own. Just fill in this formula, pause, and then take a look. And there's your answer. So the yield in this particular problem, it was 95.5%, which means about 4% of the water that should have formed. It either wasn't made because the reaction didn't go to completion, or we lost some water in the process of doing the reaction. And that's it for today.